All right, let's try this. I have not tried streaming before, so this is the first. I hope this will be recorded. I guess we'll find out. But either way, what I want to do is read a paper. And the difference is that previously I read the paper offline, and I then recorded a little 5-minute summary, and then I post that. And I'll still do that, but I thought, why not try to read the paper live? And once I read it and I understand it, then I'll record a 5-minute summary, and that'll be it. So let's see how things go. Specifically, the paper I want to read is, if I find the right tab. Oh, how many are there? 1 second. I have to get the archive ID 9199. So it's a tab. The PaLI JAMA. So I think the last paper we read was PaLI, pathways language image model, and this is PaLI-3. I skipped the second one. And let's see what it says. So the paper presents PaLI-3 vision language model that compares favorably to similar models that are 10 times larger. As part of arriving at a strong performance, we compare vision transformer models pre-trained using classification objectives to contrastively pre-trained ones, contrastively with SIGLIP as opposed to the classical symmetric cross-entropy. We find that while slightly underperforming on standard image classification benchmarks, SIGLIP-based PaLI shows superior performance across various multimodal benchmarks, especially on localization and visually situated text understanding. Scale the SIGLIP image encoder up to 2 billion parameters and achieve a new state-of-the-art multilingual cross-model retrieval. We hope that PaLI-3 at only 5 billion parameters rekindles research on fundamental pieces of complex VLMs and could fuel a new generation of scale-up models. Okay, so PaLI was a way to put there they kind of showed that scaling up, having a frozen image model that is bigger, it also gives them nice benefits. SIGLIP introduced the loss function that was much more efficient to compute. And now they're saying that they can do really well by having smaller models. And I suspect a lot of it is due to how they train them and the training data. So let's skim through. So what I usually do when reading papers is I read through the introduction. Sometimes I skim through related work, but not in a lot of detail at the beginning. Then I sometimes go to conclusions at the end, just to see what what the summary is. Then I see what the section titles are. I kind of find the most interesting things, and then I go through everything in a little bit more kind of chronological or sequential order, because I find it's useful to understand the structure and the main claims of the paper, and the introduction and the conclusion usually establish that pretty well before jumping into details. So I'll go through the intro and then conclusions, and then we'll see what to do next. So scaling of vision language models to tens and even hundreds of billions parameters has shown ever-increasing performance. Meanwhile, models at smaller scale remain critical as they're more practical to train and serve, more environmentally friendly, and support faster research cycles for model design. In the spirit of focusing on smaller scale modeling, we present PaLI-3, the third generation family of PaLI models using a pre-trained backbone with only 5 billion total parameters. We refine the training recipe and achieve competitive and new state-of-the-art results on various VLM benchmarks. Our new recipe has 3 main components. So contrastive pre-training of image encoder on web scale image data. So I guess they're using this WebLi dataset that they've mentioned before. An improved dataset mixture for PaLI multimodal training. So I wonder what's new about this mixture, and training at higher resolutions. Oh, interesting. PaLI-3 achieves state-of-the-art results on tasks that require visually situated text understanding and object localization, including 8 visually situated text understanding tasks and the refining expression segmentation task on RevCoco, along with strong performance on a wide range of classical vision tasks. So this is interesting because localization is something that ChatGPT specifically is really bad at, and PaLI-3 is pretty good at. And I've played with it, and I'll publish some stuff about it as well. But it's interesting that this is one of the reasons that PaLI-3 is good at this is because this model, the predecessor, is good at it. As part of this work, we also introduced a state-of-the-art multilingual contrastive vision model scaled to 2 billion parameters. Multilingual vision model. Interesting. Okay. Obtained using recently introduced SIGLIP recipe. So SIGLIP, if you didn't see the summary, I posted a summary of that paper as well, but it is a way to compute loss during training that is much more efficient than the standard way, and SIGLIP does not require you to do as many iterations through your batch to compute normalization factors, but by using sigmoid loss, they found a way to compute loss that still is useful for training, but just cheaper and doesn't cost anything in terms of quality. Additionally, we perform focused ablation studies to compare the classification pre-trained vision transformer backbones with contrastively pre-trained ones. This further confirms the viability of pre-training visual encoders on noisy web-scale image text data as a preferable alternative to training classification standard. I feel like we already knew that, but I guess one more experiment doesn't hurt. Our contributions summarize as follows. So we compare classification pre-trained vision transformer models to contrastively pre-trained SIGLIP models using the PaLI framework. We find that the contrastively pre-trained models work significantly better for visually situated text understanding and localization tasks. Our model achieves state-of-the-art performance on over 10 diverse vision language benchmarks while being 10 times smaller in size compared to the current state-of-the-art model. I mean, 10x size difference is not to be sniffed at, significant. For understanding visually situated text, the improvement is by a particularly large margin. Where's my tab? Here. Despite not pre-training on any video data, our model achieves new state-of-the-art on several video QA benchmarks, indicative of powerful generation abilities. We introduced 2 billion parameter VidG multilingual SIGLIP model trained on WebLi, which sets a new state-of-the-art on multilingual cross-model retrieval benchmark across 36 languages. Cool. Skip related work for now, as I mentioned. Let's go right to the end, where the conclusions are. Pretty short conclusion section. In this paper, we took a closer look at the pre-training of the image encoder in larger VLMs, specifically the PaLI type of model. By performing control experiments on that part for the first time, we clearly compared the two accounts of classification pre-training and image text contrastive pre-training, finding that the latter can lead to better and more efficient VLMs, especially for localization and text understanding tasks. This is just one small aspect of VLMs, and we hope this study and results spurs to further detailed investigation of the many other aspects of training VLMs. So I wonder if this, I mean, who knows what goes into ChatGPT, but just naively judging from Clip, which is really old by now, but it was kind of the beginning of everything. Clip was coming out of OpenAI, and it was trained on the. Oh well, no, it was contrastive training. So never mind. What I wanted to say is not right. I guess they are here showing that if you look at something like locked image training, where they take a pre-trained image model, it's better to take a pre-trained image model that is trained contrastively rather than trained for classification, which was what LIT did originally. But then they found that contrastively pre-trained image models are better. Okay, that makes sense. So that's not a dig at Clip. Really, it's just a dig at earlier versions of themselves. Anyway. Okay, cool. So we've got conclusions, limitations. So are very similar to those already presented in the literature. What is this? This is PaLI. Oh, PaLI-X. Oh, that's something new. I haven't done on this paper yet. I guess I need to look it up. Okay, but let's believe them. The limitations are similar. Okay, so now let's look at what are the sections we have here. So we've got related to work done, the model, architecture, and the training. Okay, so that's the meat of everything. And then section 4 is experiments. So they're doing classification or contrastively pre-trained VIT. Cool. Visually situated text understanding, referring expression segmentation, natural image understanding, video captioning, question answering, direct image encoder evaluation. I wonder what that is. And then section 5 is fairness, bias, and other potential issues, and then conclusions. Okay, this is kind of neither here nor there, but I'm curious what this means. Direct image encoder evaluation. Here, we aim to directly evaluate the learned image encoder without the surrounding image language model, not the full PaLI-3. All the results are in table 6. Okay. Table 6. Evaluations of the visual component in isolation without language model. Report fine-tuned classification accuracy on ImageNet, ImageNet Real, and ImageNet V2, average 0, short cross model retrieval. Okay, so this is their proposed model. Resolution 518, so that's their increase in resolution. It's still not as big as PaLI-17B, which was this from the PaLI paper. Performance is, let's see, that's not a tiny bit worse, but pretty much the same. Tiny bit worse, pretty much the same. A little bit worse. So I'm comparing against this third one, which is the biggest one. I guess PaLI-X is the, yeah, PaLI-X should be comparing against. Oh, but it's worse. Interesting. Text image. That's much better. Interesting. And then average of 8 tasks. Okay. So it's comparable. On one thing, it's much better. On average of 8 tasks. I don't know exactly what this means. Probably 8 tasks. Okay. All right. So fine. I know what the section is about. Let's go through the architecture and the training. On a high level, the architecture follows. So there's PaLI-X. VIT encodes the image into tokens together with text input, the question prompt instruction, which together with the text input are passed to an encoder-decoder model that generates a text output. Visual component. The visual backbone PaLI-3 initialized from a contrastively pre-trained VG14 model, approximately 2 billion parameters, using SIGLIP training recipe. In short, an image embedding VG14 and a text embedding transformer are trained to separately embed images and text such that a binary classifier using the sigmoid cross entropy of the dot product of image and text embeddings correctly classifies whether the respective image and text correspond. This is similar to clip and align, but was more efficient, scalable, and robust. Yeah. So this is describing SIGLIP. Okay. Text embedding transformer is discarded when inserting VIT into PaLI. So they trained the text component from scratch, which is what they've done before. Full PaLI model. The outputs of the VIT image encoder before pooling from the visual tokens, which are linearly projected and prepended to the embedded input text tokens. One more time. The outputs of the VIT image encoder before pulling from visual tokens. The sentence makes no sense to me. Are linearly projected. It's just the word. Oops. It's just that the word which shouldn't be there. Okay. So basically, they concatenate visual tokens and text tokens. Together, these tokens are passed into pre-trained 3 billion parameter UL2 encoder decoder language model, which generates text output. A text input to the model typically consists of a prompt that describes the type of task. For example, generate the alt text in some language at whatever position for captioning tasks, and encode necessary textual input for the task, answering in some language question. Okay. So training. So this is where they did some changes, apparently, to get this really good performance from a really small model. The training procedure is similar to that of PaLI and PaLI-X and consists of multiple stages. First, unimodal pre-training. The image encoder is pre-trained contrastively on image text pairs from the web. Following SIGLIP training protocol, this differs from PaLI and PaLI-X, where a JFT classification pre-trained encoder was used. We use a model-based filtering approach similar to that in Schumann. There is about, what is this? Schumann. Lion. Okay, open it. Okay, interesting. The same kind of filtering as Lion. Contains about 40% of the pairs. The image encoder is trained version 2.4. Text encoder is a 3BU2 model trained following a mixture of denoisers procedure described. And then there's multimodal training. Here the image encoder is combined with the text encoder and described in figure 1. Then, wait, where's figure 1? Oh, missed it. Review of the PaLI-3 model. Images are encoded into visual tokens individually by the contrastively pre-trained to be SIGLIP vision model. So this pre-trained model turns image into a bunch of tokens. Along with a query, these visual tokens are passed to so query is the tokenized version of this text. These tokens, 0 tokens, are passed to a 3 billion encoder decoder UL2 transformer, which produces the desired answer. Encoder decoder. So it takes the concatenated vision and language tokens and then produces a different bunch of tokens at the end. In such a setup, contrastively pre-trained model provides significantly more useful tokens than one classification pre-trained. Yep, I guess I can. I can believe that. Okay. Then this combined PaLI model is trained. So once again, stage 0 is unimodal pre-training. So they basically take the model, pre-train these models, and then stage 1. And I guess the idea, it's called stage 0 because it doesn't have to be necessarily part of this paper. Like if you want to recreate this paper, you can take an existing unimodally pre-trained backbones or towers or models, and you don't have to do this. But it is sort of required for this to work. Someone has to do it. It doesn't have to be you. Multimodal training. Let's go back here. The image encoder is combined with the text encoder and text encoder decoder, described in figure 1. Then this combined PaLI model is trained on a multimodal task and data mixture, but keeping the image encoder frozen, just like a LED, and using its native resolution. The main mixture component is again derived from the Webley dataset by heuristic filtering of the text quality and using split cap training objective. Don't know what it is, but I'll leave it for now. Further ingredients inherited from Chan et al. Are multilingual captioning, WCR, close-lingual VQA, and VQG. So bunch of different tasks, really. Notably, we do not include task or data derived from video. This was done by the X, but PaLI-3 retains competitive performance on the benchmark set in strong image encoder. We do, however, improve documented text understanding capabilities by enriching Webley with PDF documents with dense text and web images described as posters or documents in over 100 languages. So okay, cool. So to summarize, they do multimodal training, which means put the two models together, and then they have a mixture of data that represents a bunch of different tasks. I wonder if they do anything with ordering, like do they first train on all the examples that contain a certain task and then all the examples that contain different tasks and so on, or do they mix everything? That would be interesting. Maybe there's some appendix somewhere. The mixture component is yeah, okay, cool. Then resolution increase. High resolution input is widely accepted way of increasing performance, both due to making more details from the image perceptible and due to increasing model power via increased sequence length. We increase PaLI-3 resolution by fine-tuning the whole model, which means unfreezing the image encoder, with a short curriculum of increasing resolutions, keeping checkpoints at 812 by 812 and 1064 square resolution. The data mixture focuses on the part that involves visually situated text and object detection. Makes sense. Like, recognizing text is much easier in like 812 square image than it is in 224 by 224 because it's just too small and lots of text is illegible. Textualization transfer. Finally, each individual task, we fine-tune the PaLI-3 model with frozen vid image encoder on the task's training data, as described in the corresponding section. For most tasks, we fine-tuned 812 square resolution checkpoint, but for two documents, okay. So they do this stuff like up to stage 2, and then for any specific task, they do specialization. Okay, experiments. Classification for contrastively pre-trained vid. So, I mean, we already mentioned it a bunch of times, but let's just go through it. We first perform comparison of different vid models from the PaLI framework. We consider types of model classification pre-training and GFT dataset on the GFT dataset and contrastively pre-trained on the Webley dataset. We perform this experiment using a fixed resolution to save compute. Yeah, I don't think that would matter much. We further shorten stage 1 phase to 20% of the full PaLI schedule used in the remainder of this paper. The results in table 1 paint a clear picture overall, while the few short linear classification of SIGLIP models falls behind when using PaLI-3. SIGLIP models provide moderate gains on simpler tasks like captioning and question answering, and large gains for more complicated scene text and spatial understandings and tasks in RefCoco. This motivates the departure from classification pre-trained image encoders and switching to sigmoid contrastively pre-trained ones for building PaLI-3. So, okay, so what does this mean? Contrastively pre-training an image model means that you have this data set that is isn't Webley. So it's kind of weird because in LIT, the locked image tuning, they discovered if they take a classification pre-trained image model and combine it with and freeze it and then combine it with unfrozen text model and they tune, they get better results than training from scratch. And they said this is because the pre-trained classification model learned a bunch of useful properties that are helpful for these tasks. And if you continuously fine-tune it, you lose some of these properties. So that's why it's frozen and they don't mess with it anymore. But here they're saying that, in fact, it's better to contrastively fine-tune image model on the dirty web scale text image pairs, then throw out the text part, keep the image part, and then train a new, like attach a new fresh language model to it and train that, and while keeping the image component now frozen, and then train the image, and then train the language model to sort of to match it. That is kind of surprising. Like, why? I said before that it makes sense, but now I'm realizing that I actually don't know why that works. So let's go through this again. We consider types of classification pre-trained model on the GFT dataset and contrastively pre-trained on the Webley dataset. Perform these experiments using a fixed resolution to save compute, while the future classification Where's table 1? Here. Performance comparison between contrastively pre-trained models and classification pre-trained models using the same PaLI setup across a wide range of tasks. While linear classification future probing first column suggests SIGLIP encoders are worse across many tasks. When plugged into PaLI and transferred, they show clear improvements. On the most complicated and detailed image understanding tasks, SIGLIP models outperform classifier class models by a large margin. Captioning numbers are okay, so basically whenever there's a green number, SIGLIP is better. Whenever there's a red number, classification pre-trained model is better. And that's across different kinds of models. VidG14, VidL16, and B16. I wonder why captioning is worse. But yeah, I mean, quite really big differences here, and the negative differences are not so big. Okay. Visually situated text understanding. So, I mean, it makes sense that does it make sense that classification models would not be super sensitive to visually situate? Oh no, sorry. I was thinking about localization. Yeah. Actually, let's go back through this. Okay. Now, one other thing I want to verify from the beginning. Yeah. Text embedding discarded when inserting it into PaLI. So yeah, just like we said, use clip-like thing, or like rather SIGLIP. Basically, use SIGLIP. Train both image and text models from scratch. Throw out the text model, attach a new text model, and then freeze the image model, and then train the text model to match. Cool. What are the experiments we have? Visual text understanding. Okay, a bunch of references. Text understanding. The images in the dataset span a wide range of domains, such as natural images, illustrations, documents, user interfaces. For the incorrect guy, benchmark, fine-tune on the so that the higher resolution was important. Report the standard metric for each benchmark daily. So the score. Okay. Next accuracy for. The same server as for training server. Performance and vast majority of the captioning make you benchmarks, but okay, not super interesting. So okay, I think we've got a good idea now. We don't have to go through all the benchmarks. So let's see if I can do a 5-minute summary. So this PaLI-3 vision language model shows how you can train a vision language model that is 10 times smaller than competitors, but performs better than them. And specifically, they use the SIGLIP formula that we've talked about before, and they combine a contrastively pre-trained. So this is a bunch of things that we talked about before are now coming together. So first was lit, where they discovered that locking the image model and training the text model gives good results. Then there was SIGLIP, where they discovered how to make the loss computation more efficient. Here they're putting these two together, but in a funny way. So in LIT, they took a vision model that was pre-trained for classification. Here they're taking a pre-trained vision model, but that pre-trained vision model comes from contrastively training using SIGLIP. So the procedure is, first, you take your WebLi dataset. So this is the really big dataset of text-image pairs. You start from scratch. You initialize the weights randomly, and you train the vision language model using the SIGLIP formula, which was described before. Once you're done training, you keep the image model, you lock it, and you throw away the language model. You delete it, don't need it anymore. And then you take a new language model, you attach it to this pre-trained frozen image model, and you start training that. And here they have also not just used the original WebLi dataset, but they, I think, created a different mix of it with a bunch of different tasks, and discovered that they get really good performance. So one of the main contributions, or maybe even the main one, is proving or showing that using a model that's contrastively pre-trained is better than using a model that's pre-trained for classification. So that's kind of surprising. Cool. And I think that is it. That'll be a summary. So I think we're done for now. I'll now end the stream and see what happens. And afterwards, record a little 5-minute summary. Thanks, bye.